Well, thank you. It's really a pleasure to be able to make some personal perspective comments on high resolution X-ray spectroscopy, which I've devoted my career to. And I appreciate the opportunity to do this. I'm going to talk a little bit about rewards, but mostly about challenges, because that's what really has been where we spend most of our time. And we've heard about some of the challenges already at this meeting. The rewards are that high resolution spectroscopy, whether it's in the X-ray or any other band, puts most of the physics into astrophysics. And we've seen that already at this workshop. But after you go through this schedule of talks, you can see that the 3 days that we're spending here is proof of that fact, that those are the rewards. So you're all talking about the rewards, and I'm not going to say much more about them. The challenges have been prodigious. Spectrometers are always hard to build in any waveband, but I think the X-ray presents some special challenges. Of course, when you're doing high resolution, you spread the signal out into a lot of energy bins or wavelength bins, and then you get photon starved right away. So one of the real challenges has always been to get sufficient throughput to match the spectral resolution. We've already heard, in fact, also from the laboratory physics community that data analysis and theory and modeling become much more complicated. Getting more physics out requires putting more physics in, and the theory and modeling will remain very challenging. I guess that's job security. One of the concerns, though, is that this is a high sort of barrier to entry for many people. And I think that's one of the challenges for our community, is to make it possible for more people to get engaged. Since if you're going to try to get, a few $1 billion out of your government to build a spectroscopy mission, you want to make sure that you have a significant community of people who are going to make the most of it and use it. And that's been another challenge, a political challenge that we've always dealt with. Well, by virtue of wave-particle duality, I want to make just a few comments about spectrometer design. And I know this is trivial physics for all of you, but I think it's an interesting way of looking at it. Spectrometers compare incoming radiation to some physical standard unit. You can treat it as a wave and compare the signal to a unit of length, like the crystal spacing, lattice spacing of a crystal through a Bragg crystal spectrometer, or a grading period of a reflection or transmission grading. Or you can treat it as a particle and compare it to a unit of energy, like the band gap in a CCD. And that measures the energy and is called non-dispersive measurement. Actually, for the HETG, we use both, which I think is a nice thing to say to freshman physics course. We treat the radiation as a wave to measure the primary wavelength, but then we use the non-dispersive measurements with ACES for order sorting. So it combines the two of them. It so happens that given the nature of things, wave-particle duality crosses over in the soft X-ray band, so that if you're below or about a kilovolt, you really have to treat the signal as a wave to get adequate resolution. And above that, it has to be treated as a particle. And this is can be seen in this chart, this graph, which actually was shown this morning, much to my surprise, because it's pretty old. But you can see that the dispersive spectrometers do better at long wavelength, and so their resolving power, which is what's shown here, resolving power versus energy or wavelength, their resolving power increases from right to left, whereas the particle detection of photons increases from left to right. And of course, we now have an actual mission that's about to be launched that's going to fill in that gap. But it's important to realize that we still, because of just the sizes of the fiducial energies of atomic scales or of energies of even the microcalorimeters, the characteristic scales, we need to have both kinds of spectrometers to cover the X-ray band. And that's just, where we are given in nature. Well, I'm not 100% sure of this. In fact, maybe somebody in the audience knows better. But I believe that at least the first detection that I know about of a line from a non-solar X-ray source was made by a rocket flight of the University College London group when they detected just barely the oxygen 8 Lyman alpha line from the supernova remnant Puppis A. This was 15 years after the discovery of SCO-X-1, which just shows how hard it is to make these measurements. And it was a prodigious job to get as far as they got. And I think none of us would be satisfied with that kind of a detection these days. So here's 50 years of satellite-borne X-ray spectrometers. The attempt to do Bragg crystal spectrometry was valiant, but not too fruitful until Einstein, and even then it wasn't that impressive. And then, of course, you can see from ASCA on the CCDs, which I would say would be, moderate resolution spectroscopy, not high, have been the workhorse detectors. And then the microcalorimeters, we hope now, are going to finally come into the fore. To put this in context, Uhuru was launched in 1970, just before, a few years before ANS, the first mission on this chart. About a year later than that, in 1971, I came to MIT, hired by George Clark to design and build a focal plane crystal spectrometer for Einstein. He hired me regardless of the fact that I was a freshly minted PhD from experimental particle physics, who didn't know anything about X-rays, had never built a spectrometer, and didn't know any astrophysics. So I guess I was perfect for the job, but the Einstein Observatory was the first telescope for non-solar X-ray spectroscopy or X-ray astronomy. It carried the focal plane crystal spectrometer, an objective grating spectrometer, which was we would now call a transmission grating spectrometer, and the solid space spectrometer from the Goddard group. There were some pioneering observations that were made with this mission. And you can see, for example, this spectral scan of Puppis A, which now has a more respectable, can I use this, more respectable measurement of the Lyman alpha line, for example, the oxygenate Lyman alpha line, and an early detection of the famous helium-like triplet, just to the left of that. It was clear that while we could measure some spectra of the brightest sources, that we needed to do a lot better than this to really make progress. And then just about the time Einstein was flying, a miracle happened as far as I'm concerned. And that is that by absolutely pure chance, I was in an idle moment leafing through some MIT literature, and I discovered that there was a professor of electrical engineering and computer science named Hank Smith, who was working on making X-ray Fresnel zone plates. And I had no concept that that was even conceivably possible. So I called him up and tried to find out more. And it turns out that long before nanotechnology was a household word, Hank was working on pushing to smaller and smaller feature sizes for VLSI technology. And for a while held the record of the smallest transistor. My student, Mark Schattenberg, who was working on Einstein, fell in love with this technology and went to work in Hank's lab, trying to perfect the fabrication of transmission gratings, which is what in the end he did. So little did we know that that chance occurrence would end up with a 20-year timeline of development of what turned out to be the HETG. And some of the major milestones are listed on the side there. But it was a long and tortuous path, but one full of challenges and challenges overcome. The key requirements that we were working towards are listed here. To get high spatial resolution, we needed grading period of 200 nanometers. And that's, of course, smaller than the wavelength of visible light. And it was pushing, even then, very much the state of the art of the VLSI industry. We also needed to be able to maintain precisely a period from one facet of degrading to another, because there were hundreds of facets needed to fill the aperture, and you had to have them all the same to better than 200 parts per million in order to keep the resolution as high as we wanted to achieve. And then we needed to get high aspect ratios of the grading bars to make sure that we had high efficiency for the gratings. Let me elaborate on that. That little inset there shows X-rays striking the grating, going either through the gold or through the spaces between the gold bars. And the gold attenuated the X-rays somewhat, but they still penetrated. But they also were phase shifted because of the imaginary part of the index of refraction of gold at those wavelengths. And that meant that the X-rays going through the bars and through the spaces between the bars were 180 degrees out of phase, if you tuned that length right enough. And then they would give you destructive interference in 0th order, and most of that power would end up in the 1st or higher orders. So you end up with a grading efficiency shown by those bumps over here that are higher than the lower curve, which is what you would have for just an opaque grading. And so we were able to tune and increase the throughput, and that was a very important requirement. So how did we get these requirements, or how did Mark and his team get these requirements? I use we in the collective sense, because most of this was really done by Mark and his team. The first step was to use precision UV interference lithography to get that 200 nanometer spacing. And as you can see here, there was a UV interferometer, which is shown on the left, and the 200 nanometer product shown on the right. The plan was to use this to make a mask, and that mask would then be replicated hundreds of times to make the final gradings, and so that they would all have the same period. Then the next step would be to use X-ray lithography, an intense beam of X-rays in the laboratory. This is not the X-rays that we're going to measure later. And to replicate that mask into a grading, and to do that hundreds of times. So to do that in a finite amount of time, we needed a high-intensity X-ray source, which was what industry also needed, but they hadn't really developed one yet. So we found a startup company which was building high-intensity X-ray sources, and put an order in for one for $3.5 million, which they happily accepted. And then we prayed that this would arrive on time for us to be able to make the gradings to meet the Chandra schedule. But that wasn't to happen. In 1993, the company that was building this high-intensity X-ray source went bankrupt. We had already paid them $1.7 million, which was something that a bunch of lawyers at NASA noticed. And you can ask me later how I avoided jail time for this, but we were, this should have been a death blow, because we were literally within months of having to start building gradings when this happened. But Mark had spent so much time understanding every aspect of lithography to make the masks, that he realized that he could turn the masks into the gradings and make them all using a standard grading to get the grading to grading variation low, and deep re-ion active etching to get the deep high aspect ratios that we needed, and to do all that within the time scale allotted. And so, in fact, 3 years later, we delivered to NASA the full complement of HETG, HEG, and MEG gradings. And we were on schedule and on budget. So in 1999, of course, Chandra was launched with the LETG as well as the HETG. A few months later, the RGS was launched on XMM Newton. And I think the real era of high resolution X-ray spectroscopy was inaugurated, and it's been 25 years approaching now of success. What's next? We already know about. I've heard many references to Chrism, which is going to fill in that gap in the resolving power energy scale, and it's going to be particularly powerful because of the fact that it will achieve its highest resolving power at the high energy portion of the window near the iron line complex, which is so important. But meanwhile, the dispersive folks aren't sleeping. Ralph Heilman and Mark Schattenberg have been developing some really remarkable advanced gratings called critical angle transmission gratings, where the grating operates in higher order, and so you can get resolving powers of thousands to tens of thousands, and with high throughput, and using anisotropic etching to make these remarkable structures that you can see here. And this is baseline for Arctis, among others. And I think you're going to hear about that on Thursday, hopefully a little bit from Randall Smith. So back to the rewards, which I didn't talk about too much, but I wanted to make this a more personal statement about the rewards. It's been, for me, a 50-plus year career of working with a team of extraordinary scientists, engineers, students, and staff. And we've been doing what George Clark, when he hired me, said was being paid to have fun. So I thank all these people, and it takes a village. Thank you.